So let's start on problem 4 right after problem 3. And that's because I already answered this question in problem 3, because I found out that the points of order 3 were the points of inflection. So, and maybe I only thought about that because I had seen this word sometime earlier. But who cares? So there are 8 other points of inflection. We already have noticed that the point of infinity has reflection. Notice they occur in symmetric parts. So that means if x point y is a point of reflection, then x point minus y is as well. Now, that was omega 1 and omega 2, and then the points there. So, so if this is 1/3 omega 2, then this is 2/3 omega 2, and that means that rho of 2/3 omega 2 equals, then we subtract omega 2, the Weierstrass P function, minus 1/3 omega 2. Then we use it's even. So that means they map to the same x value. And doing the same for derivative, then the derivative is odd, so it's minus. So they change sign. Be they real or complex, they change sign. Find an equation for the x-coordinates. I was thinking about this part of the night, really. I didn't fall asleep very quickly, and then I thought of a way. I didn't really think very much about it. It kept turning around in my head. So I found one way of doing it the natural way. I'll show you in a minute. But I also spent some time on the net looking for ways to find inflection points. And they only had the answer that I was taught with parametric curves. If you have a curve x plus y as a function of t, then it's the cross product of the derivative and its second derivative must vanish. Then we have an inflection point. And since we have an algebraic curve and not a... So I couldn't use any of the stuff I've learned. So what I did instead was to say that we must have a point of inflection. So now that came out totally wrong. We must have a point which have contact of order 3, not just any tangent has contact of order 2. So a point of inflection has contact of order 3. So that was what I did this morning. And I actually did it not to solve problem 4, but because I wanted to make a plot showing that I could find the points of inflection, so that I could make it geometric picture of what was going on. So first we define the polynomial, then we write up the equation of a tangent at capital X, capital Y. So we have a point capital X, point capital Y on the curve, and the equation, this is the equation of the tangent, that this vanishes. And then that x point y, or minuscule x point y, lies on the curve. It's just this one, the minuscule letters. And then we must solve these two. And I thought the most simple way to do it was to eliminate y, because you can just isolate y here and then insert it here. Of course we do it in a more elegant way, but basically. So then we get this equation. And x to the 6th occur, and y squared and y to the 4th. But as x, it's a tertiary equation, and we would like it to have only one root. Now, we want to get away with y, and it only occurs in even powers, so that's easy. So when that is eliminated, we get this. So it's all right. It's a polynomial of order 3. And since it's a tangent, then it should be fulfilled for capital X. Nice. Actually, it always has contact of order 2. We need, for it to be a point of inflection, it needs to have contact of order 3, and this means that this guy must vanish. And so we just set x to capital X, and then we get a 4th order equation which is easily solved, discriminant being something 27. And so there are 4 solutions, and with this simple polynomial x to the 3rd minus x, 2 are real and 2 are imaginary. And then when I find the values of the second coordinate, this is nicely complex. These are real, connected to that, and these are are imaginary. But the real part of the curve we can actually map or plot. So I plotted them. First I make an implicit plot of the elliptic curve, and then I calculate the formula for the tangents and plot them, and then we map them together. So the curve is red and the tangents are blue, and they actually touch at the point of inflection. The red curve comes in below and exits above. So this method works. I have found the points of inflection. So the next step was to try the same method with all the curves coming from the congruent number problem. And it turns out that we just have to multiply by n, so that's really simple. And the y values by n to 3/2. Then I tried this guy with the Weierstrass P function. That became intractable. So one of the solutions is given by this, and we notice the discriminant occurring several times. But apart from that, it's not a simple expression. Now, we had to do it in general, didn't we? In case, find an explicit form. Oh, I have done that. So that was the first one I did. Or the second one, rather. Mind you that I ask Mabel to assume n is positive. That makes the solutions here much more simple. So I guess this is really the answer. Then we need to show that they are never rational for any n. But that doesn't really scare us, because this is clearly irrational. So whatever we multiply it with an integer, it remains irrational. And so do the others. Ha! So, time for my afternoon tea.